Hello students. This is a brief reminder about how a titration is set up and works, specifically pertaining to acid-base neutralization reactions in Chapter 4 of Zumdahl. A titration is a volumetric analysis. Volumetric because the amounts that we will be documenting, the data that we are collecting, are volume measurements. We do not blindly go into a titration. We know what reaction we are accomplishing, be it an acid-base reaction or an oxidation-reduction reaction. For example, let's say that we encounter an unknown concentration of a calcium hydroxide solution in the back stockroom. Well, we know that calcium hydroxide, being a base, will react with hydrochloric acid to create water, written as HOH or H2O, and calcium chloride. What we can do is react a known concentration of hydrochloric acid with the calcium hydroxide in order to find out its concentration. Usually, the unknown is placed into a flask or a beaker, and we will know the volume of it, let's say 20 milliliters. Now here it has acid, but let's pretend that it's base. And we've added it into our Erlenmeyer, so we know the volume, but we do not know the concentration. What we add to the burette will be what we call the titrants. We will end up knowing the total volume of titrant that we add. So if we know the reaction, we know, for example, that we need, let's just say, 52 milliliters of this hydrochloric acid. We will know its concentration. Let's just say it's a 1 molar solution. And then, of course, knowing the reaction, we can then calculate what the concentration of the calcium hydroxide is. We know when the titration is complete when we have reached what's called the equivalence point or the stoichiometric point of the reaction. Whenever, in this case, we have added enough of the acid or the titrants to completely react all of the calcium hydroxide. We've satisfied the mole ratio per the amounts that we have. So we've added, in this case, enough acid to equal the amount of base that we had in our flask. We usually use the aid of a pH meter to identify the equivalence point or an indicator. Probably, the go-to indicator for us is phenolphthalein. Oh, heavens. I'm not even going to try to spell that. It's just a crazy spelling, which we know is clear with acid and slightly pink with base. An indicator is chosen so the indicator's end point. The end point is the pH in which the indicator changes color. So we want the end point, the pH of that, to be approximately the pH of the equivalence point or the stoichiometric point. Just some other terms. HCl is a monoprotic acid. It has the capability of only donating one hydrogen ion per molecule. Sulfuric is an example of a strong acid that's diprotic. Phosphoric would be an example of a triprotic, but that's a weak acid, of course. So to get into our example. The example that I had in our packet. An environmental chemist analyzed the effluent, or the released waste material, from an industrial process known to produce the compounds carbon tetrachloride and benzoic acid. Benzoic acid is a weak acid that has one acidic hydrogen per molecule, a monoprotic acid. A sample of this effluent weighing 0.3518 grams was shaken with water, and the resulting aqueous solution required this much sodium hydroxide for neutralization. Calculate the mass percent of benzoic acid in the original sample. So, the benzoic acid was dissolved in solution. We are told that 10.59 milliliters of 0.1546 molar sodium hydroxide was required to reach the equivalence point. So, our reaction would be NaOH plus HC7H5O2. We know that this will be a 1-to-1 mole ratio. We will get HOH plus NaC7H5O2. We are told that 10.59 mils of 0.1546 molar hydroxide was required to react all of the benzoic acid. I imagine that an indicator like phenolphthalein was used. It would begin clear. We would add enough base until we got the slightest tinge of pink. That means we've reacted all of the acid and we are just barely basic. The ending value that we're seeking is the percent of benzoic acid in this waste. Now, we're believing that the benzoic acid is the only thing there that reacts with the sodium hydroxide. Remember, a mass percent will be a mass ratio, in this case of the benzoic acid that our titration will tell us is there, compared to the mass of the whole of the effluent. All right, so we're trying to find this. So if we start, we have 10.59 milliliters of the sodium hydroxide solution. I want to get it to liters so that I can use my molarity as a conversion factor. For every 1 liter of NaOH, there is 0.1546 moles of NaOH. Now it's a 1-to-1 mole ratio. And now, because I know what I'm trying to find, I just need now to get grams of my benzoic acid per mole, and that actually is 122.14. So, doing that, I get the answer of 0.1999 grams of my benzoic acid. That is what will go here. Doing my math, and with sig figs, it is a 56.82% benzoic acid in the effluent. Please see me with any questions.